Hello. In this video, I'm going to try to provide a foundational understanding of why Docker exists and where Docker fits into computing and computers overall. Why is it important and what's the history of containerization? So, at the most basic level, you have your physical computer. This is your computer hardware, which is made up of physical computer components. These are physical chips and other physical devices that are made in a factory and leave the factory together. And once they've been created, they can't be changed. They are somewhat constant over time. Unless you're going to change a component or do some welding at a very small level, you're not going to be changing your computer hardware. At the next level, you have computer firmware. Firmware is represented by these zeros and ones on this chip here. This chip is, for example, a ROM chip, a read-only memory chip that would be part of your computer's hardware. And on that ROM chip, we call it read-only because we typically only read the programs that are zeros and ones on that chip to do certain tasks using the computer's CPU. But those programs are very infrequently changed. We don't often install firmware or uninstall firmware. We just update it very infrequently if we absolutely need to. And it will essentially control the computer's hardware, start software, and talk to software so that it can provide functionality for the devices that are part of the computer's hardware. Next, we have software, of which there are many types. One type of software is the operating. We have Windows, which is the Windows NT kernel. I'll talk about kernels in a bit. We have Mac, which is the XNU kernel. We have different distributions of Linux, which all share the Linux kernel. And then we have as many other operating system kernels as you like, such as FreeBSD, which then runs an operating system on top of its own custom kernel. So operating systems in turn will run application software. Applications include graphical apps like Chrome, Google Chrome. They include terminal apps like the ZSH shell or the Bash shell. They provide virtualization type 2 hypervisors like VirtualBox. They also include web servers like Nginx or Apache. And they include container manager software like Podman and Docker. So all these applications will just run on your operating system. And the way that this works, because the firmware is responsible for starting software, it will decide which operating system or which disk containing an operating system will start up when your computer is turned on. So maybe you have an Apple computer and you have Mac OS installed. So Mac OS is the single software that will control all other software on the computer. Now, macOS has certain applications you might be familiar with, like it has the Finder application, or it has the terminal application, and there's a default terminal installed called ZSH. So ZSH and the Finder in Mac are simply application software. They may come packaged with your operating system software, but they themselves are not the core of the operating system. So what is the core of the operating system? Well, it's this thing called a kernel. So operating systems split software execution, which is essentially just zeros and ones at the lowest level. They split execution into kernel mode software and user mode software. So kernel mode software is privileged software that interacts very closely with the firmware for the device and allows the hardware of the computer to be utilized by the operating system as well as by all of the user software and applications that are installed on the system. So kernel mode is very special in kernel mode. There are certain actions that are restricted, so the operating system can only do those actions and run that type of code itself. And so when we want to do other things, we have to talk to the kernel, even if we are an administrator on the computer. So a common misconception is that being the root user is the same as running code in kernel mode, but that's not true. The root user is simply a normal user on the computer that has extra special privileges to do certain things. And regular users are even less privileged users who may be even restricted further from the root user. So users run in user mode and kernel runs in kernel mode. And the operating system kernel provides abstractions to user mode programs that allow them to do useful things like talk over the internet or manage files and things like that. So managing files is actually a super critical aspect of operating systems. Operating systems typically provide some type of file system that programs can then interact with to do lots of different things. On Linux, for example, the file system starts with a root of // and then there are subdirectories like home and bin and etc, which stands for etc. Bin stands for binaries. Inside your binaries, you might have the Chrome file or the Nginx file or the Docker file, which are executables. You might have the etc folder with a config file under there. And you might have a similar structure on Windows, where you have the C drive, and C has users, and users have home folders, and there are program files for executable files that like programs essentially, and then program data might contain configuration for those programs. And on Linux, everything is essentially abstracted to a file, whether that's network communication or the processes that are running on the CPU through the operating system, USB devices, everything is a file in Linux. So the file system is very critical to understand, and it's a core functionality that the operating system is providing. Now, even though the Finder application on Mac is running in user mode, it will ultimately talk to the kernel so that the kernel could do things like saving data to a file that you would try to create with the Finder. And the kernel is super tightly controlled, and that keeps your computer from crashing because there are not very frequent changes to that type of code, even more so than firmware, but less so than most application software. And that way things don't really go wrong as often, and user mode programs can't corrupt your system as easily because they have to talk to the kernel. So what happens when you run programs, you might install Chrome on your system to have a web browser, and you might install Bash because you don't like the ZSH shell that comes with Mac, and you might install Docker to run containers, and you might install Nginx to run a web server in the background. So all of these things are talking to your operating system, which is macOS, and using the kernel, which is the XNU kernel. Now, you already have seen how the system configuration here has changed. So think about when we had none of these programs, like none of these, and we just have macOS. If we have the same version of macOS as someone else, our system configuration is very similar when we start out. But then we start installing programs and things start to diverge. So now our systems are different, and if we try to share activities or actions that we do on our computer with someone else, it's not necessarily going to work the same for them. So we have this very specific set of programs that are installed. And we also have a problem that certain things that happen when programs run have an effect on the file system. Because the file system is so critical, a program has its choice to run in non-privileged areas of the file system and place files there on behalf of the user. So let's say Chrome has a config file at etc config. Nginx also chooses to have a config file at etc/config. Now that's not really true in the real world, but let's just say it is. Now they're both writing to etc config, and Chrome, that's a file managed by the operating system. And so Bash will talk to the kernel and ask to edit config, and Chrome will talk to the kernel and ask to edit config, and they'll edit the same file. And then what Chrome does will mess up Bash, and what Bash does will mess up Chrome. So that's not a very good scenario. We'll get to how to solve that in a bit. But when it comes to the base operating system, you can install any operating system that you like, whether that's Mac OS or some distribution of Linux like Ubuntu, and then you can go and run your user's application software on top of that operating system. And these configurations become very tedious to get consistent between different setups. So not only is my physical hardware going to be different, my firmware might be different, my operating system might be different, and then I might install software in a different order and install different software and change the files in my file system. You see where there become millions and billions of possibilities for how to configure this particular computer when it comes to software. And all those changes are changes to the state of the computer. So when we install a program like Proxmox, which is an operating system, we have an advantage. So when we're installing, say, Ubuntu or Mac OS, we can't have Mac OS and Ubuntu running on the same computer at the same time. We have to have only one operating system that can then do other things, do other application tasks. So Proxmox is an example of a type 1 hypervisor. There are others as well, but Proxmox is just an example, and it's based on the Linux kernel. And what Proxmox allows you to do, as do other type 1 hypervisors, is it allows you to create virtual machines on your physical computer. So you can take your system resources, say you have 8 gigabytes of RAM and 4 CPUs and a 1000 gigabyte hard drive. Think of the screen real estate on this cartoon computer as the resources of this computer. So as I change the size of these little boxes, I can change the size of these virtual machines that I'm creating with Proxmox. And so typically, traditionally, virtual machines are fixed in size. So I might say that this virtual machine is going to get, say, on this one physical computer. So they think that they have their own file system from their own operating system. They have their own kernel in that operating system. They have their own programs installed on them. So we could go and on this Mac installation, we could go install Chrome. And that Chrome is different from, say, the Bash that we have installed on Ubuntu. And so if they go and edit that config file that was, say, at /etc/config, I might have one of those on the Proxmox host operating system, and I might have one of those inside this virtual machine, and I might have one inside of this virtual machine, but this file is its own file. It's different from this one, and it's different from this one, because these are all three different logical computers. There's the host operating system, which has its files, and then there are these other operating systems that have their files. So if Chrome goes to edit config and Bash goes to edit config, those aren't going to conflict with each other at all. Now, I mentioned how these traditionally have been fixed in size. So I want to allocate this much of my system resources, and you get a problem where when you have many of these virtual machines, then your system resources start to get used up, and you can only create so many VMs before your system slows down, and then you also run out of resources to run programs on your host operating system. So say you just want to run an Nginx server on your host, you're going to have to leave some resources available for that. But more recent virtual machine platforms actually allow dynamic sizing of these resources so that they can sort of shrink down when they're not using too much resource, and they can grow when they then need more resources. And that's an advantage that wasn't on Binder, and we like how things are in Mac OS. So we go and install Mac OS as our operating system, and then we install a Type 2 hypervisor on top of Mac OS as an application. Now we can get that same virtual machine feature, but it's on top of our existing operating system. So we get to keep our Mac OS operating system, and maybe instead of Chrome we use Safari, but we could install Chrome as well as another application, and then we can have these virtual machines where we can have, say, Ubuntu, and we could have FreeBSD on another one. And the advantage to using virtual machines in this situation is that each computer in these black rectangles thinks it's its own computer, and it installs its own kernel when we install an operating system. So when we install FreeBSD, this is FreeBSD kernel. When we install Ubuntu, this is the Linux kernel. And the host system is the XNU kernel. So these are separate kernels. It's creating sort of an inefficiency in the sense that we can't all draw on one kernel, but it's creating a capability in the sense that even though these kernels are different, we can always maintain these systems on the same physical device. So containers work a little bit differently. So what is a container and why is it different from a virtual machine? So we're going to take the example of Ubuntu as a Linux distribution. And so Linux is special because it is an open source operating system kernel on which a lot of operating systems are based, and it's had a lot there have been a lot of developments in operating system software that have come out of Linux. And so one of those is a alternative approach to isolating programs or applications that run on an operating system. So let's say we had that example of Chrome engineers. While virtual machines date back to as early as maybe the 1960s, a little bit later in the 1970s, operating systems engineers thought, well, what if we can just virtualize the software environment and not run it in a virtual computer? So they thought, let's just draw a box around these computers, just like we had with the virtual machine. And we can either run something inside the box, or we could just run it on the host system. And then when we go to use, say, a file, then there's the host etcconfig. There's the isolated etcconfig for this bash instance, and there's the isolated etcconfig for this Chrome isolated instance. And so while this Chrome that's installed right on the operating system with no isolation would just use the operating system's single config file, this Chrome thinks it has a fake file system where config is something unique. So it gets its own unique config, and it gets its own unique config for bash. But these programs still interact with the main Linux kernel. So there's no kernel inside of here, and at this time there's no operating system inside of here. It's just a program running in an isolation where it's given it's lied to and told that it's in its own space where no one else lives, even though it's really running on a system where other things are running as well. So it provides security as well, in a way that this program can't mess with this one and vice versa. Now, this idea continued to develop over time in the Linux operating system, and we started to add more and more capabilities to what these isolated environments for programs could do. Now, this didn't mean every program was necessarily isolated. We can still take, Ubuntu and install Nginx and run that server, but we could choose to use the operating system's capabilities to create these isolated environments. And we started to not just be able to isolate files, but into the 80s and 90s and 2000s, developers of Linux started to make isolations for network interfaces and physical devices, and essentially every aspect of what it means to be a program and interact with the operating system. And there was so much capability there that eventually you could pretty much run an operating system inside of one of these little isolated environments. So say you want to run CentOS. Since you're essentially just virtualizing the file system, and CentOS, the user experience part of CentOS, is centered around the file system, they thought, well, let's just have CentOS but no kernel, and then you can run that and share the kernel with the main Linux operating system. And then this CentOS can go and install Nginx, or it could go and install Chrome. And this is kind of the origin of what containers are. They're like virtual machines, except they share a kernel with the operating system. And this very closely was developed out of the Linux operating system. And this, while very powerful and completely a native feature of Linux to create these types of containers, the interface for doing this got more complicated as the features of containers became more advanced, and as additional components were added to the operating system to support this concept of a container, it became more cumbersome to do it manually. And so container management applications such as Docker, which came out around 2013, sprung up to be an application interface between creating containers and the operating system itself. So Docker says it'll take care of creating these containers, and it'll do all of the hard work of talking to the operating system to do so, but it'll let you share a kernel between these different containers. And that's essentially still what Docker does. Now, another thing that Docker will provide is a way to run containers also on Mac and Linux, or Mac and Windows. So you might think, well, you said that the Linux kernel right here is shared with these virtual operating systems here and here that can run their own programs in their isolated environment. And that's true. But because this Docker and other container management platforms made this concept of the container so popular, they provided ways that you could actually use a non-Linux kernel as your base operating system. And that's not strictly true, because what they would do is when you install a container management application like Docker, we'll delete Docker, or another example is Podman. Docker is not the only container management software. Then what this software will do is talk to the Mac operating system and say, can I have something that resembles a Linux kernel? So on Mac, it's a sort of virtual Linux kernel, and it's a way of essentially having a Linux kernel but on Mac OS, because the Mac OS kernel is not Linux, it's XNU. So Podman will work with the operating system to create this virtual Linux kernel so that it can run containers. And that allows you to take Linux kernels like CentOS, or Linux containers like CentOS containers, or say a Ubuntu container, and then just share the kernel with the Mac virtual kernel that Podman helped to create. And so we don't need a kernel within there like we would in a virtual machine. And so this is more efficient because not only, as with modern VMs, can these sort of scale up and scale down as we need to run more programs on the operating system. Not only do we have that, but we're sharing a kernel with the host system, so it's more efficient because we don't have to duplicate kernels. That only downside is that that kernel always has to be Linux if we want to run Linux inside of the container. And Windows has a solution for this as well. So whether it's Podman or Docker that you're using to orchestrate your containers, Windows, you might notice, also does not have a Linux kernel by default. So Microsoft developed the Windows subsystem for Linux, and there's a Windows subsystem for Linux version 2 at this time, and WSL2 allows you to do different kinds of things with Linux operating systems in Windows, but it also is something with which Podman or Docker can communicate. They also have other ways to interact with the Windows kernel, such as Hyper-V, which is a Microsoft virtualization platform. But WSL2 is the main kind of recommended way to use, say, Docker or Podman to create containers that are Linux containers on the Windows operating system, which is a non-Linux operating system. So it has this WSL2 kernel, kind of like macOS has, and then you can go and run those same Linux containers on Windows. So what about FreeBSD? Can I run FreeBSD in a container? Well, no. Why not? Because it is its own type of kernel. So Linux is kind of this special type of kernel that is so foundational that it's supported on Mac and Windows and Linux, but FreeBSD is just not used enough to be widely adopted. And so they're looking into, for example, for FreeBSD to allowing some sort of configuration like this, where you could have a Linux kernel that could talk to Linux containers. But as far as I know now, it's not possible to have FreeBSD either as the host of the system or as a container itself. And that's because it uses a different kernel. And so it is important that when you're creating containers, the kernel needs to match the kernel for the system. And Windows has a special way it can run, where it can actually run Windows containers, where the kernel is shared with the Windows kernel. So what do I mean? Let's say these containers are now Windows containers instead of Linux containers. We now don't need the WSL2 backend for Docker, and we can simply use Docker to create Windows containers. Now the catch here is that this is only available in Pro and Enterprise versions of Windows. So for example, I have Windows Home. I don't have this feature, but normally in Docker Desktop, if you go to the widget in the taskbar, you would see this somewhere around here to switch to Linux containers or switch to Windows containers. And it switches your entire Docker installation to run one type of container over the other. And that would allow you to install Windows inside of a container and then run programs. Say you want a program that is only supported by Windows, like maybe if Chrome was only supported by Windows and not by Linux, which it is, then you could easily create a container and run that application inside of the container. Like I said, the catch here is you need certain versions of Windows, and you have to completely switch your system between Linux and Windows containers. And this is a specific feature of Windows that is not true of other operating systems. So if we go back to our Linux configuration from before with the WSL2 backend, which remember is like a special Linux kernel for Windows, then we can run our Linux containers again, like we're switching back. And what we can do now is run this, like I said, on any operating system. So because Linux is Linux, we could run CentOS as our host, and then we could use Docker to create Linux containers. We can install Windows, as you just saw, and run Linux containers, and we can install Mac and use the special virtual Linux like similar to on Windows to run Linux containers on Mac. And you might think, well, do they have something similar with Mac where you can run XNU containers but only on Mac OS? And the answer, as far as I understand, is no. Currently, Mac supports Linux containers, but there's no such thing as a Mac-specific container. And while Windows containers may be useful for software that's only supported on Windows, most software tends to be cross-platform, or it tends to work, if anywhere, on Linux, depending on the type of software that you're looking at. And the advantage of that, obviously, is that Linux is an open source kernel, and the advantage is that you can run those containers that you create on any type of system. So while we have this disadvantage that compared to virtual machines, we need some way to have our host system have the Linux kernel available, we have the advantage of performance because these containers then all get to share that kernel with the host system. And so essentially that is the gist of why Docker exists. It is a way to manage the relationship between an operating system, a host operating system, and containers. And most often that refers to Linux containers. Although there are technically Windows containers, most of what you're going to run is Linux containers. And that gives you a ton of options because there are a ton of different Linux distributions that you can use to run all kinds of different software. So I hope this has helped to understand a little bit about how computers work. They're based on hardware, firmware, then controls the hardware and starts software. Operating systems are the base of all software that runs on most computers, and applications run on top of operating systems. You have type 1 hypervisors like Proxmox that are operating systems and can in turn run virtual machines containing other operating systems with any kernel, including FreeBSD, Linux, Windows, or Mac. Then you have type 2 hypervisors which run on other operating systems. For example, you could have Linux or Mac and then install VirtualBox on top of it, and you can then in turn create virtual machines like that contain, say, FreeBSD or Linux or Mac or Windows, because the kernel is contained inside the virtual machine. Finally, you have containerization, which originated from Linux and the Linux kernel and native capabilities that the Linux kernel provides. But container management platforms arose to solve the complexities of creating these virtual execution environments for software, such as Podman and Docker. And now that we have those softwares, there are application interfaces for containerization that allow us to talk to a Linux kernel on Mac OS, a Linux kernel on Windows, and a Linux kernel on obviously any type of Linux to run Linux containers anywhere. So we gain an advantage that we can run lighter weight containers that share a kernel with the host system, and we lose the advantage of virtual machines that we can have each virtual machine have its own kernel, such as a FreeBSD kernel. We also covered how operating systems tend to run special privileged software in kernel mode. Then they give privileges to an administrator user or a root user to do certain privileged actions outside of kernel mode. And then they give regular users even fewer privileges in user mode as well. Most operating systems are structured around file systems that follow metaphors from file cabinets with nested files and folders. And those may be different across operating systems, but tend to follow the same kind of metaphors. Those file systems then create very unique states on computers that make virtual machines and containerization appealing to keep programs that run in user space as applications from interfering with each other. And so we can isolate them in different ways, whether with virtual machines or containers, so that they can have their own isolated execution environments and have their own virtual network interfaces, files,